Hi everyone, my name is Victor Wang, and today I am presenting ShadowCrystal's third seminar on drone theory. ShadowCrystal is a nonprofit organization, or at least upcoming one, that is dedicated to expanding engineering knowledge as well as more practical theory. I have done lots of drones both practical and theoretical, and I'm going to ISEF and publish research on it. Today's seminar will go over basic components of drones as well as some of the more impactful physics concepts that govern the flight of drones. So as you're watching along, make sure for some of the questions that are laid out throughout the slides, you can answer them in your head or do something similar. And that way, before I say out the answer, you can have an idea of what do you think the answer is. So before I get started yapping about drones, I think that it is quite important to first understand of why do we even care about drones at all, right? Because like why should we care? Period. Well, drones are, and the industry itself is like $50 billion, so it's kind of a big deal. But more specifically, we have a lot of applications for them. You can use drones to like fertilize or take videos of crops. In this image over here, we have a drone with a camera attached to it that can like scan pests or like analyze crops, for example. Drones can be used to deliver packages. Like, for example, Amazon is experimenting with drone delivered packages and stuff like that. And you can also do lots of other logistical uses like shipping and stuff like that as well, especially in hard to reach areas. Drones can be used for surveying. Essentially, if you want to map out like land, mountains, but in a really difficult to access area or something like that, that's where drones are useful, especially if you want to find people, right? Nowadays, many rescue agencies are using drones with infrared cameras in order to search and rescue people that may have gotten lost. And as a more particular example, for the Ocean Cleanup, which is another organization dedicated to cleaning up trash in the ocean, they're using drones to map out plastic in the water, right? So that's just an example of what drones can do. Drones can be used to take just photography of just like a cliff, mountain, stuff like that. Sometimes with practical use, but also just looks kind of cool, to be honest. And also we have just the recreational use. And this is probably the most common for the average person here. So I'd like to ask, what have you guys seen drones used for? For example, FPV racing, right? FPV racing is where people control drones first person and fly them in very aggressive races. And it's an example of how drones can be used recreationally. But yeah, think about it, because I'm sure almost everyone has probably at least seen one application of drones, and that's why they're important. So now we're going to get started with some of the more technical parts of this seminar, starting off with the parts. In a drone, there are many different parts that are kind of like human organs in a certain analogy, and they make the drone actually work. We have parts such as the flight controller, the battery, the electronic speed controller, otherwise known as ESCs, motors, and propellers, which all work together to actually make the drone fly. Just like how in a human, all of your organs make you like stay alive. Which means that throughout the remaining few slides for the parts, I'll keep a helpful analogy on what each of the parts is similar to in like human terms. So starting off, we're going to have the drone frame, which is kind of like the human skeletal system, or more simply just the bones. So this is the most obvious part of the drone, right, as it might seem. But in reality, there's quite a bit of engineering behind it, because weight is everything for a drone. And this is one of the themes that you will see throughout all the different parts. They are all optimized for weight. In this case, the drone frame can account for a big portion of the total drone mass. And since drones need a lot of power to stay afloat, lighter materials are very important. This is why you will see drone frames with plastic, carbon fiber, or other lightweight materials. Now, the drone frame itself consists of a central body where all the sensors, batteries, flight controllers, stuff like that stays in, and then 4 different legs to give space for the motors, which are mounted on particular mounting holes on the arms. And of course, the propellers attached to the motors. The central body is advantageous because this allows for the wiring to be relatively simple, at least simpler, because the parts are physically close to each other. Except for the motors, propellers, and the ESCs, which are not mounted in the central body. Just as a little fun fact, one of the common lightweight materials, carbon fiber, is surprisingly conductive, which means that if you do not account for that and you lay material parts straight on the carbon fiber, you will get short circuits. But just to summarize, the drone frame is essentially the core of a drone, and it is the structure, so it holds all the parts together. It is made out of a lightweight material and consists of a central body which holds most of the parts, the 4 legs, and the motors. Now let's take a look at one of the smaller parts that is still very important, which is the flight controller. The flight controller is essentially tasked with taking in data from all sorts of different sensors and human commands and radios and stuff like that, and doing lots of math to determine what the drone should do next according to those commands and signals. Finally, it then sends its own commands to different sensors and parts of the drone to make the drone do whatever it thinks that the drone should be doing. Now, remember the weight thing, right? Flight controllers are also lightweight as well, and this is why we typically see small computers. We don't see crazy like PC type computers. We see lightweight ones like the Raspberry Pi, the Arduino, or more. Some flight controllers are not pre-programmed with anything really, like this Pi Zero. This means that we have a lot of customizability, but we need to code our own flight controller or take somebody else's flight controller essentially. Other ones, like the Pixhawk, are pre-programmed, which means that they work right out of the box and are most common for use in racing drones or stuff like that. However, it's not as easy to customize specific components. While these computers may look small, in reality, thanks to modern semiconductor technology, even the smallest of these computers can do plenty of calculations required for a drone to work. Most of drone theory is math, and if there's one thing that computers are good at, it is math. To summarize, the flight controller is essentially the brain of the drone. What it does is that it takes in signals, just like how the brain takes in information from your eyes. It does lots of calculations to determine what the drone should do next, and then it sends out commands to make the drone do whatever it thinks it should do. Now let's talk about one of the parts that it is very visible and the purpose is pretty obvious. The motors and propellers. They make the drone fly, right? What they do is that we have input power. Technically, it should be more complex. I'll go over that in a couple slides. And then the motor then takes in this power and spins a propeller mounted on it very, very fast. We're talking 100 times per second. It's so fast that to the human eye, it looks like a blur, which is why they can be very dangerous because you may not notice a propeller spinning until they hit you, which is not good. They're also very noisy. But what the propellers, like their main goal is not to destroy things, but their goal is to actually make lots and lots of lift for the drone to stay afloat. What's going on is that the drone motor, the propeller, pushes down on the air as it spins because the propeller is curved. The curved propeller pushes air downwards, and by pushing air downwards, the entire drone receives a force upwards, lift, which then helps the drone to fight against gravity and stay afloat. The detailed physics, including Newton's third law, will also be covered in shortly down the line. But for now, what you need to know about motors and propellers is that they take in power, spin a propeller, and the propeller pushes downwards air, makes lots of lift, which then pushes the drone upwards. However, it does mean that these motors are very dangerous because they have to spin at very high speeds. So always take precautions when working with motors. For example, never stay close to a motor which is on and it has propellers. And even when there are non-propellers, you should still keep caution. Also, they are safer. Now, before talking about some of the more complex electronics and electricity concepts, it may be useful to go over a review of electricity as well as one of the most common formulas that talks about electricity because it is a core concept, Ohm's law. Ohm's law basically says that voltage is equal to current times resistance. But what do those words mean? Well, a useful analogy in that case might be to, let's talk about them, just like how salmon swim upwards. If you don't know, salmon will swim very aggressively back to where they were born. And in this case, they can kind of be like the electrons that are actually flowing through a circuit. Because in reality, electricity is consisting of electrons, which are microscopic particles that you cannot see, and moving through a wire or something that allows them to move in a circuit, which is electricity. But for here, we'll talk about salmon swimming upstream. If that is the case, then voltage is essentially the intensity or the motivation or the power in which the salmon are swimming upstream or electrons are being pushed. Current is very simply just the rate of which electrons are flowing or salmon are swimming. And finally, resistance is how difficult the conditions are for the electrons to move, or in salmon terms, how difficult the swim is. For example, what obstacles that could make a salmon like have a more difficult time swimming would be like faster moving water that's fighting against the salmon, a longer swim, or water which is denser and is thicker. And just like in electricity, we have similar things. Longer wires have more resistance. Wires that have higher resistance just like are more difficult for electrons to flow through, have more resistance as well. Just to summarize, this means that voltage equals current times resistance, where voltage is the intensity in which electrons are swimming, current is the amount of electrons flowing, and resistance is how difficult the swim is. We will now apply these concepts to analyze another part, which all has to do with electricity. The electronic speed controllers. Hey, at least the name is fitting, it's electricity and all that. Well, ESCs are devices that turn in DC voltage from the battery, use a lot of fancy circuits and switching, and turns that into three-phase power that is used for a brushless motor to spin. Okay, that was a lot of jargon. Let's break it down. Something that I didn't mention, but is over here, and it's very important to know, is that drone motors are brushless. So motors come in two terms, brushed and brushless. Brushless types essentially do not have a central brush. Wow! But what that means is that there's essentially no physical component touching the shaft. And that means that there's less resistance, which is great because it means that the motor can spin faster, but it's bad because due to complex physics, essentially, you cannot use a constant power to get the motor to spin. Instead, we need changing power, and that's what three-phase power is. So the battery will produce constant voltage power. Remember voltage, right? The intensity of which the electrons are moving. So the voltage is constant, but we need the voltage or power to actually have changing voltage or phased power. So that is what the ESC is actually doing. If you look over here, there are 4 cables in the input. A red cable, which is the main voltage, right? Then the black cable, which is the ground, and the white and black cable, which are the signal and the signal ground. More on signals later. But the ESC has 3 different outputs, right? And that is the three-phase power. That these ports can then be connected to a motor via wires. So if we were in an ideal world, this conversion would be 100% effective and we would have no waste heat. Unfortunately, we do not live in a perfect world, which means that they make a lot of waste heat, the ESCs specifically. The ESCs have their own resistance, and we can measure the amount of current, and via this equation, we can find that heat is equal to R times I squared. If you need a refresher, look back to Ohm's law. And this means that the higher current that flows through an ESC, the more heat that it makes. And more heat can cause the ESC to melt, have melted connectors, melted wires, fried components. Generally not great things. So now, take a moment to think about this. What do you think will happen to these 20 amp ESCs if we continuously pull 30 amps or even higher? Feel free to pause the video and think about it. Well, while it's impossible to be 100% certain without testing it, we should not test that because it's very likely for the ESCs to have problems because they're melted and they don't work anymore because their connectors are fried. So we generally should respect the current ratings on ESCs. Just to summarize, ESCs are parts that take in constant voltage from the battery, use a lot of fancy switching circuits to make it into phase power, which is required for brushless motors, which are most drone motors, required for them to spin. More specifically, they make three-phase power, and you can see that by the three prongs over here that are carefully timed to push the motor shaft around and around and around via magnet interactions. However, they are limited to a certain current because, as we can see over here, higher current will lead to much higher heat, and that can cause serious problems. Now, remember the signal cables, right? Well, how do they work, these ones? Well, the way that most signals for PWM works is that we use PWM. PWM stands for pulse width modulation. The way that it works is that we essentially send pulses of power hundreds, if not thousands of times per second. Each pulse consists of a very short phase where the power is on, followed by another very short phase where the power is off. By controlling what percentage of the total pulse has the on power, we can then encode a signal to whatever we're trying to send, because the receiving receiver can essentially decipher how long the on phase was or find an average power. In the drone's case, a higher duty cycle, which is what the on percentage is called, typically leads to higher thrust, and therefore the drone will go upwards. However, we need to note that this is not being directly fed into the motors. The motors do not receive a signal. The ESCs receive a signal. They have to use this signal and account for it, basically, to change the three-phase power which is being sent to the motor. So by changing the three-phase power, physics will take over and the motor will change the thrust accordingly. Now, let's look at a more concrete example. This is actual data that I gathered for one of my projects. And as you can see on the bottom, we have throttle. So throttle is an abstract term that is typically controlled by the user that represents the amount of power we want, but it is not a direct value that is used in the drone. Instead, we have to convert it to duty cycle, which I've already done here. And as you can see here, we go from around 54% to 58%. On the left, on the y-axis, we have thrust in grams. 1 gram of thrust is the amount of thrust required to hover 1 gram. So with this relation between duty cycle of PWM and thrust, what can we do with it? Well, now we can do some math. Let's say a drone weighs 800 grams and has 4 motors. This means that each motor has to support 200 grams of weight in order to make the drone hover. So if we want the drone to hover, each motor needs to make 200 grams of thrust, which is around this line. So if that's the case, then what throttle do we need to give the motor in order for the drone to hover? Think about it, and feel free to pause to run the math. If you're curious, the answer is around this blue point, because that is where the line hits 200 grams. It's around like 56.4%-ish. Now let's take a look at a more complex example. Similar, same drone, same thrust relationship, but now we want the drone to accelerate upwards. So we want the drone to actually go up at 1 meter per second squared. Now, for simplicity's sake, we can assume that gravity is just 10, which is everyone's favorite physics assumption. And now we want to add 1 meter per second squared additional, which means that instead of 10, we want 11 meters per second squared, which is 10% more thrust. If we want 10% more thrust, the 200 grams of thrust that we used to need would be more like 220. So with 220 grams of thrust, what throttle do we need to produce it? Again, feel free to stop the video, think about it, and then continue playing it once you think you have the idea down. So now we need 220 grams of thrust because we need to accelerate upwards at 1 meter per second squared. And since G was 10, now it's 11. So 220 grams is around 57.2%-ish. Here are the detailed numbers: 56.4% initially for the hover and 57.2% now for the ascent. This is expected, right? It's important in engineering to do sanity checks to make sure you actually did your math correctly. So common sense will tell you that higher throttle, that's more thrust, the drone should be going up, right? So conversely, if you want the drone to go up, we need more throttle. And in this case, that's correct, because in the first case, we want the drone to hover, right? That's 56.4%. Now we want the drone to go upwards, accelerate upwards. Now it's 57.2%. So the increased thrust is correct. The increased throttle matches what we expect. So now let's continue our exploration of the different sensors in the drone. One of the common sensors that are used to help the drone detect its position and orientation is an IMU. And robotics kids here might be salivating these words or hating these words, but you might be familiar with them. IMUs measure orientation. Compasses also help. Both voltmeters measure battery voltage. More on that later. Barometers measure altitude. So just as an example of how an IMU works, just one of the sensors, an IMU consists of an accelerometer as well as a few other sensors. But the way an accelerometer works is that they measure the direction of gravity. Now you might be saying, well, gravity is just down, right? Yes, but more importantly, the sensors measure the direction of gravity relative to a couple predefined directions, which means that by detecting how much gravity there is on each of the axes, it can do trigonometry and calculate the orientation. This is used on a drone to tell the flight controller on the drone which direction the drone is, and therefore what should it do to correct for it if need be. This is just one of the sensors that are used. There are many other types of sensors, but this is just a quick example. In a human, this would be like your eyes helping you to orient, or surprisingly, humans also have similar accelerometers. They're fluid and they're in your ears, right? But this is why you get dizzy, because the fluid in the ears, which are kind of like a human accelerometer, shake around, which confuses and makes you dizzy. So similarly, a drone has a physical component, like an IMU, which has an accelerometer, which is doing the same work. And finally, on our list of parts, we have the battery. The battery is pretty simple. It's just, well, that's not true. There's a lot of chemistry, but we're going to ignore that. Just say that it's a big box of power, because it basically is. Well, big boxes of power causes big boxes of responsibility, right? these batteries can easily catch fire, especially the high energy ones to save weight. Remember, a common theme, right? So we need special storage bags to store the LiPo batteries that are very commonly used in drones. These batteries are very energetic because we want to save weight. Now, another interesting property is that the voltage is that the voltage and capacity are in a tight relationship. So you can see down here where note that the x-axis essentially stands for how much drained power, and the y-axis is the voltage. So these curves over here mean that by measuring the voltage, we can determine how much power has been used. And then when the voltage gets low enough, we can tell the user to land the drone now because the battery is almost out. As you can see here, once the drone battery nears its final legs, right, it's almost out of power, the voltage will suddenly crash. And once it crashes, your drone will not stay in the air. So this is basically can be used as a low battery warning. As power is being drained, the voltage drops, which is normal. And then right before, as the battery is completely exhausted, the voltage crashes to essentially zero. So here's a problem for you to think about. If a LiPo cell is charged to 4.2 volts, the blue line, what voltage will it be at before it crashes as all the power is used? The answer is around 3.6 volts. As you can see here, this is right about just before the voltage rapidly drops as the battery is completely drained. So this can be combined with a voltmeter, one of the sensors that I just talked about, in order to measure battery voltage and therefore determine capacity that has been used, essentially. So now we're going to start talking about the concepts of drones. One of the concepts, which is surprisingly underrated, in my opinion, is wiring. Because I've been talking about all of these sensors and components and stuff like that, but you need to actually connect them for them to work. In this specific example, we are assuming that the Raspberry Pi is a flight controller, and this is an IMU sensor, which has a bunch of different pins that are signals. Well, we need the first four. This IMU could have an accelerometer, just like the one that I was talking about over here. But it could be any sensor. This is just an example. The exact type is not important. So the Raspberry Pi has something called GPIO pins that are where we can connect the wires. The VCC on this sensor is the input voltage. The GND is the ground, where basically electrons flow from here to here and then go back to the ground via the ground. SCL is the synchronization clock that is used to tell the sensor basically the timing that it should send data out. And finally, the SDA is the physical data from the sensor itself. So the flight controller can request data, and then SDA will return the data to the flight controller, and then it can use that data to determine what the drone should do next. You sometimes do need to be a bit careful about what sensor you're using, because while most sensors do not use lots of power, some sensors like LiDARs can use a lot of power and overload, basically burn a GPIO pin. So we need to be directly connecting them to a stable power supply. But in general, this is a pretty common way of wiring components. You look at the pins that you need. You probably want to search it up, right? And then you connect them to the pins on your flight controller. And just like that, you have a connection. So for the final section of today's seminar, I'll be talking about physics, right? Oh, but it's important. Newton's third law is a classic law, which it's one of the core principles, right? Any action has equal and opposite reaction. Wow. Well, now we can finally apply it. Let's say that for here, we have a strong anchor to something, an arm, which is relatively light, and a motor, which is attached to the edge. Now, let's say the motor is spinning up clockwise. Well, Newton's third law says that any action has to have an equal and opposite reaction, right? So the equal and opposite reaction in this case would be the entire motor trying to spin in the other direction that it is spinning up in, because there has to be some other reaction, right? So now, since the motor is spinning up clockwise, what do you think will happen to the entire arm? Because the anchor is fixed, right? So the arm is going to spin somehow to counteract the clockwise rotation of the motor. So which direction do you think it will spin in? Clockwise or counterclockwise? Feel free to stop the video here and think. The answer is counterclockwise because the motor makes clockwise torque as it is spinning up. And as it makes clockwise torque, the motor spinning clockwise will force the entire arm to have a counter torque, which is counterclockwise. So it's the opposite, right? Newton's third law. Clockwise acceleration of the motor causes counterclockwise movement of the entire assembly. This is a real problem for drones because it means that if we cannot fix this, the entire drone will spin uncontrollably. Here's an example. We can now apply another principle which is derived from Newton's third law, which basically says that the spinniness or angular momentum is conserved. Angular momentum is a bit more complicated than just the spinniness, but it's close enough. Now, it's always conserved, and this is where the problem starts, because it means that our clockwise motor, right, if it spins up clockwise, then that's clockwise angular momentum. So we have to have something spinning in the other direction to counter it out, because initially we had none, right? Then the motor started to spin up, of a command or something like that. So something's going to have to spin the other way. Well, that has to be the entire body. And this principle means that we can't really stop it. Well, there's an exception actually. We can use multiple motors. Because while one motor is going to spin in a fixed direction and cause everything else to spin in another, there's no principle that multiple motors have to spin in the same direction, right? Here's a diagram of a helicopter. Now, I'm sure many people have seen helicopters, but don't actually know why they have the tail rotor, right? Because the central rotor is pretty obvious. It spins up in the right. It spins up clockwise or whatever direction it wants to spin in, and makes lift, blah blah blah. But why the tail rotor? That doesn't even make the helicopter go up. Well, it turns out that because the helicopter blades are spinning in a certain direction, it makes a counter torque, just like how the example over here did, right? We have the counter torque. Well, the way a helicopter stops it is that it has a smaller tail rotor, which generates its own torque by spinning a bit, and its own torque then cancels out the primary torque from the helicopter blades, resulting in a stable system. You might be wondering, well, doesn't the tail rotor make its own torque too? Yes, but the center rotor can then be adjusted slightly to counter it. So by combining two motors, we're now able to have a stable system that can generate lift. But this is obviously not how drones work, because helicopters are also not a shining example. They're very complicated, right? So how could we adapt a similar idea to a drone, right? We do need multiple motors, so what can we do? Just as a fun fact again, some helicopters do actually use two main rotors in opposite directions, which makes counter torques and that cancel each other out and therefore do not need a tail rotor. I wonder if we could apply a similar principle. We absolutely can. So a drone has 4 motors, right? And if we make 2 of the motors spin in the other direction, the torques that they make will perfectly cancel out the main motors, and therefore we will have no net spin. Even better, we can actually change the thrust of each of the motors to adjust the drone's direction and position via just thrust changing. That is an incredible achievement, because when you realize that helicopters, the way that they change the direction is via very complex mechanisms in the propeller blades, the fact that we can just change the thrust of the motors to make the drone change directions is very awesome. And this is also why we have 4 motors because any less and we cannot do this. So just to elaborate on my claim, how do we actually change all directions of a drone without even having to move the motors? Now, like roll and pitch seem pretty easy because in this diagram, we can just increase the thrust of 2 of the motors to make the drone flip over. But how do we get to even rotate? That doesn't make any sense. We don't have any propellers in that direction. So unlike the helicopter example, we cannot just have a tail rotor which turns it. We don't have anything like that. But there is a way, and it depends on the torques that the motors generate. Remember that the more thrust that a motor makes, the more counter torque it generates. So we can use that to our advantage. Also, take a look at this diagram, right? Clockwise motors on one direction, diagonal, and counterclockwise on the other direction. So, you think you figured it out yet? Let's see. The diagonals is very important in this case because by increasing the thrust of 2 of the motors opposite to each other, they make more of a torque, right? Because more thrust, more torque. Now, if we decrease the motors of the other direction, we stop the drone from going upwards in general and decrease the counter torque that is opposing the torque increase. So we actually get the drone to rotate even more. And even better, all the other parameters are controlled because the altitude is not changing and we're not going forward or backwards or anything. So we can individually control each of the directions. And this is a really big advantage of drones because with the very simple design of fixed motors, we can control all directions by just changing thrust and taking advantage of Newton's third law. Just to recap, because this is a very important concept, a motor spinning in a direction, like making torque, will induce a counter torque that will spin the entire body, including the motor, the other direction, thanks to Newton's third law. Conservation of angular momentum means that we cannot just like stop it with a single motor, because like if the motor spins one direction, angular momentum must be conserved, so something else has to spin the other direction. But we can have other motors spin in other directions, and that generates counter torque, if that makes sense. And that cancels out the counter torque made by the other motors and results in the drone not spinning. We typically have this diagonally set up so that if we want to make the drone spin in a certain direction, we can increase the thrust of motors diagonal to each other. And that induces a rotation without having the drone fall over or tip over, which would basically be a rotation in the other directions. So this is how a drone with fixed motors and no motors pointing in the yaw direction is able to control all of its directions. Now, just to have some fun, let's look at a couple examples of drones that a drone that I've actually built, and we'll see how control is actually used. So behind the scenes, there was a lot of math going on, but also a lot of the physics being applied here. Because once the computer detected via the sensors that I was talking about, and that the drone is off angle, it then applies the concepts of counter torque to essentially correct for that. So that's an application of the physics that we were just talking about. The flight controller can use data from sensors, detect off angle, do math to correct for it, and then change the thrust of the motors accordingly to get stable flight. So what happens if your flight controller is not so well coded? Unfortunate things can happen.
都在转，我能看他们4个都在转。
Very unfortunate things. Yeah, let's just say that that's not a good outcome. But that can happen if your flight controller has poorly coded software, or if your sensors are fried, or a combination of all those, which is what happened in this case if you're curious. But this is why we need to have tested software, and we need to actually understand the physics of what's going on. Unbelievable. But with that, we have come to the conclusion of the seminar. Thank you, everyone, for listening and listening to this recording. If you have questions, you can feel free to ping Tristan or me. So my Discord username is Crazy Flying Duck. So you can add me as a friend or like DM me if you're curious. But this is STEMinars. So we are running them from ShadowCrystal to increase STEM outreach and also teach people just interesting concepts. And we get into the nitty-gritty details and really teach the engineering that is used in them so that you can apply them and use them for where you need to know these principles. So if you're curious about more STEMinars in the future, you can contact Tristan or join our ShadowCrystal Discord to be able to see future announcements for STEMinars. But with that, thank you for listening and have a nice day.